Welcome to my new calculus channel. My name is John Gabriel, and today I'm going to show you how you can do exact arithmetic with ratios in geometry, but you cannot always do this in algebra. So let's begin. So let's look at a few examples. So if we have two ratios, and I've got a little reference here of the examples I want to do. So the first ratio is going to be this ratio. Let's see here. And the second one is going to be this ratio. Okay, so we've got two ratios, this ratio here and the bottom ratio. Okay, as you see over here, right? So now we can plot these ratios as follows, like that, and then we can find a common consequent using similar triangles. So if we just position these points, the green and the magenta point, like that, then these solid dotted lines are the antecedents of these ratios when they are expressed using the same common consequent. So in this case here, the common consequent is this line here. So if we had to extend these like that, and well, first of all, if we extended this by that much, we would have to extend this to that length, and similarly, if we extended this to this length, then this would have to be quite long, right? But I don't really want to do that. So let's just bring this back here again and just leave it as that, and this as it was, like so. Okay. So now, as you can see, if we use algebra, we do this in terms of the abstract unit, but this ratio of magnitudes is equivalent in algebra to what you see over here, to 6 divided by 2, because they have the same consequent, right? Which is, in this case, just 1. And of course, we could move these to coincide anywhere along the x-axis. Now, that's one example. Now, if you had to do something like this, and you said that, then these don't have the same, or the same consequent. So we can see here that the ratio of these is actually 3 in algebra. And how? Well, we could easily find out why that is the case if we can do it in many ways. We could, for example, make this consequent the same as that one, or we could make this consequent the same as this one, right? Doesn't matter which way. So if we extended this one here to be the same as this one, then we'd have that result, right? Which is still, again, the same. It doesn't matter. And we could move this along here, and same result as we had before, okay? So it doesn't matter which consequent or which proportional ratio you decide to choose in order to calculate the quotient. Now, what if you had a quotient like this, circumference to diameter and square diagonal to side of square? So let's do this. Let's say we have this here. Say about that much. Oops. Something like that. And make this that. Okay, and then this guy here, let's make it somewhere there. Okay, something like that. If we show numbers, then this is still too large. There, that's better. So now, what I'm actually getting at here is that if you plotted the circumference of a circle on this line and its diameter on this line, and the diagonal of a square on this line and the side of a square on this line, then you don't have a measure in algebra. This measure here is not actually correct. So and neither is a more accurate, so to speak, measure. So for example, you said pi divided by root 2, okay, is equal. So as you can see, it's approximately right, but it's in geometry, this ratio here is exact. This is the exact quotient. So if you had the quotient of that non-existent magnitude pi or number, pi is actually a constant. It's not a magnitude nor a number. And the same for square root 2. It's neither a magnitude nor a number. And I'll explain to you why in a second. Because we can find any proportional ratio to these ratios, okay? As you can see by these parallel lines, okay? This ratio, the first one, is proportional to this y length to this x length, right? And similarly, the second ratio is proportional to this long y length to the second y length. So this again is the same expression. It's the exact quotient. But if you try to do this in algebra, you cannot, because algebra uses the abstract unit, okay? So in geometry, we're always using a consequent, as you see this bottom line here, which takes the place of the abstract unit. And of course, the quotient is just simply the ratio of the two antecedents, right? As I showed you earlier. So for example, if you had 2 divided by 2, or let's say 2 divided by 1, and divided by, let's say, a half. 2 divided by a half is 4, right? Okay, so, and if you reposition these as follows, there you go. You'll get the exact answer. So what I've shown you in here is that you cannot do algebra on just any particular magnitude. So algebra only works with the abstract unit, and that's what Euclid did in Book 7 when he took all the properties of arithmetic from geometry, as I've just shown you, and transferred them through to algebra using the abstract unit. So this is an important video because you get to see how to do this, the exact arithmetic calculation in geometry, which you cannot do in algebra, okay? So I'm going to leave it at that. My name is John Gabriel. Please subscribe if you're not a subscriber already. And I'll place a link to this applet in the details section, and also a little short note of what I've just explained to you so that you can study it in your own time. If you haven't clicked like, do so. Tell your friends about this channel. And I'll be chatting with you again soon. Till next time, goodbye.